Hello guys, so this is chapter 3, part 1. Still part 1. Then the last video, right? We stopped right here. Was the molecular weight of water and what's the molar mass of water, H2O. So you saw that it will be the same value, right? Just change the unit. So for the molecular weight, it will be 18 atomic mass unit, and for B will be the molar mass will be 18.016 grams per mole, right? Right. Now, the mole relationships. So what you learned previously was 1 mole of anything, of any particle will be equal to 6.02 times 10 to the 23 atoms, or molecules, or ions, right? Okay, so 1 mole is equal to Avogadro's numbers. That's 6.02 times 10 to the 23. If the question says like moles of atoms, moles of molecules, or ions, will be 1 mole equal to Avogadro's number. And for example, atoms, molecules, or ions. Okay, so 1 mole of atoms, ions, or molecules contains Avogadro's number of those particles, right? Avogadro's number, this number here, right? Right. The number of atoms of an element in a mole is the subscript in a formula, like the number of atoms of that element in the formula times Avogadro's number. So why moles? So you are to convert like from grams to moles, you take the grams given, divide by the molar mass, and using moles calculated here, we are going to use the Avogadro's number to convert it from moles to atoms, for example. So the moles provide a bridge from the molecular scale to real world scale. In using quantities, we can convert it from mass to atoms or from atoms to mass. So, for example here, calculate the number of hydrogen atoms in 0.350 moles of C6, H12, or O6, right? Okay. So the first step, let's start with what was given, right? Here. 0.350 moles, right? Of C6, H12, O6. You know that what? Each 1 mole, right? Of C6, H12, O6 is the Avogadro numbers of this molecule. So 1 mole of this molecule, you have Avogadro's number here. Molecules. But the question is not asking for molecules. The question is asking for atoms of hydrogen, right? So we know that each 1 molecule here, how many atoms you have here? 12, right? So 12 hydrogen atoms, correct? Okay, now let's calculate it here. So we are going to calculate 0.350 times 602 right? 0.350, 6.02, 23 times 12 will be 2.53, right? Times 10 to the 24th atom of hydrogen, right? Okay. The next topic is about percentage composition. So how you find this? The percentage of each element is equal to the number of atoms times atomic weight divided by the formular weight of the compound, that means the total formal weight, times 100. So for example here, let's calculate the percentage of carbon in ethane. So ethane, the formula for ethane is C2H6. So what's the molecular weight here? So you know that you have a carbon, right, and hydrogen. How many carbons you have here? 2 carbons, right? And each carbon is 12 or 11, right? Atomic mass unit. And you have 6 hydrogens here. And each hydrogen is like, can use 1.01. And then we're going to adapt here. And the here should be like 30.07. So the molecular weight from ethane is 30.07. This is the total here, right? So percentage of carbon. How much carbon we have in this formula here? What's the percentage? So first, that's how much carbon you have here. How much the percentage of carbon? So you have 2 carbons, 2 times 12 or 11, divided by the total molecular weight of this molecule times 100. So you're going to see here, calculated it to be 75.887%, right? Okay. And then the next topic here is about empirical formula. So empirical formula is the smallest ratio of a molecular formula, right? Molecular compound, molecule. So the steps are, first, like the question mostly will be given in percentage here. I think the resolution is better now, right? So the empirical formula, the questions about empirical formula usually will give in percentage, so the mass of percentage, and assuming that the total is 100 grams, the same number in percentage will be the same number in grams. So like, for example, here, the compound of this compound here has 61.21 percentage of carbon. So carbon, it's 6, it says, oh my gosh, 0.31 percentage, right? So actually gonna be 61.31 grams. The same thing with all here. So this step here, all percentage will be converted to grams because we are assuming the total is 100 grams. So hydrogen is 5.14 percentage, right? So it will be 5.14 grams. Nitrogen is 10.21 percentage. So it will be 10.21 grams, correct? And then finally, oxygen that says 23 point percentage, so it will be 23.33 grams. So you are this step here. Now, use the molar mass, you are going to find the moles. So to convert from grams to moles, we are going to divide grams by the molar mass. So let's divide here everything by the molar mass. Okay. What's the molar mass for carbon? 12,011, right? So 12,011. And let's divide here, right? 6 to 1, 6 to 1.31 divided by 12.11. So we have 5.10 moles of hydrogen. So we're going to do the same thing with hydrogen, nitrogen, and oxygen, right? So hydrogen is 101, so divided by 1, right? Grams per mole here. What should they say here? Grams per mole, right? Here. Grams per mole. And so what's the molar mass for nitrogen? Nitrogen is here, right? 14.07. And for oxygen, it can be like 16 here. So now let's find the moles of everything, right? So the moles, for example, here, is about 5.09 moles. The nitrogen, how many moles here? Let's divide 10.21 divided by 14. We have 0.7289. And then oxygen, let's divide it for 23.33 divided by 16. Moles, right? So you have here moles of carbon, moles of hydrogen, moles of nitrogen, and moles of oxygen. So you have here the moles of each element. Now, the next step is calculate the mole ratio. How are we going to do that? By dividing all by the smallest. By the smallest mole number. So which one is the smallest here? 0.7289, correct? So let's divide everything here by this one here. So 5.104 divided by 0.7289. So here, right, 7, I'm gonna write the closest, the whole number here. This one gonna be about the same, 7. So I'm dividing here, right? All by the smallest one. So dividing all by this number here. So if you divide 0.7289 by 0.729, we're gonna be 1, right? And then finally, there's one here. If you divide 1.4, 1.456 divided by 0.7289, we're gonna be around it 2. He was divided all by the smallest, so divide everything by 0.7289. Okay, so what's the empirical formula here? What will be the answer? I mean, carbons, 7 carbons, hydrogens, 7 hydrogens, nitrogen, 1 nitrogen, and 2 oxygen. So this is the answer for this question here, the empirical formula, right? So remember, if you see gram percentage, we're going to convert it to grams using the same value, just change the unit. The last topic here for this portion, chapter part 1, is about molecular formula. Remember, the number of atoms in a molecular formula is a multiple of the number of atoms in an empirical formula. So if we find the empirical formula and know molar mass for the compound, we can find the molecular formula, right? For example, here. This hydrocarbons has empirical formula of C3H4. What's the molecular weight for this empirical formula here? So then, in experimental, we determine the molecular weight is 100.1 atomic mass unit. The question is, what is the molecular formula? So let's start with this one here. What's the molecular weight for this C3H4? So C3H4, we have 3 carbons, right? So for the carbons here first, carbons, you have 3 carbons. Each carbons, I'm gonna round it here to 12. And in hydrogen, have 4 hydrogen, and each hydrogen is around 1, right? So grams per mole here, to atomic mass unit in that case here. So what's gonna be the answer here, right? So if you do this calculation, here should be something around 40, about 40. I mean, I'm around here, atomic mass unit. The question is, what's the molecular formula, right? So to find this, we need to find the ratio. How calculate the ratio? Are you going to take the molecular formula weight divided by the empirical formula weight, like the weight, the molecular formula of the empirical one. Yeah, sorry. Okay, so here, can you understand here? Is the resolution okay? Okay, so if you divide this by this, what's gonna be here? Ratio is equal. The molecular weight of the molecular formula is 121, right? Atomic mass unit. And the molecular weight of the empirical formula is or about 40 here, correct? So if you divide the base by this, the closest whole number will be 3, right? That means if the empirical formula is C3H4, your molecular formula is, so C3H4, multiply everything by 3, it will be C9H12 kind, because we are going, the ratio between empirical formula and molecular formula is 3. So this is chapter 3, part 1. Let's go to chapter 3, part 2. Okay, so the first thing is we needed to balance chemical equations, right? Right, and the chemical equation, you have the reactants and the products. You have the coefficients, right? The physical state in parentheses, and the coefficients. The coefficients here, if you talk about molecular interpretation, it means 2 moles, two molecules, there's two, coefficient 2. 2 molecules of hydrogen gas, 1 molecule of oxygen gas, making 2 molecules of water. And in a molecular interpretation, we have, in the mole level interpretation, we'll have this 2 also means 2 moles of hydrogen gas, 1 mole of oxygen gas, making 2 moles of water. So, in converting from moles to grams, we are going to multiply by the molar mass. For example, each hydrogen is 1 gram, right? How many hydrogens you have here? The total here, like you have 4 hydrogen here. That means here you have 4 grams of hydrogen. Converting to grams from oxygen to grams, each oxygen is 16, right? So 16 times 2 will be 32 grams of oxygen. So initially we have 4 grams of hydrogen plus 32 grams of oxygen. That means in the reactants we have 36 grams for reactants. And in the product here, you have 2 moles of water. Each water is 18 grams per mole, right? So if you have 2 moles of water, it will be 2 times 18 grams per mole. That will be 36 grams per mole. Oh, sorry, 36 grams of water here. So the conservation of mass, you have 4 grams plus 32 grams equal to 36 grams of reactants and 36 grams of products, right? All right, so there's a coefficients in front here, the compounds, right? The molecules. They represent the moles of each react and product, and also the molecules. Depends on the interpretation. Also may represent the molecules of each reactant and product. All right, law of conservation of mass. The law of conservation of mass indicates that in an ordinary chemical reaction, matter cannot be created or destroyed, right? And no change in total mass occurs. And the mass of products is equal to the mass of reactants. So here, like I showed you here, right? The total mass of reactants is equal to the mass of products. So for example, in this reaction here, we have a sulfur making this silver sulfide here. Right? So you are going like, for example, if you are mixing the two reactants, the total mass should be, of the product should be the sum here, correct? Right. Right. So reading equations in moles. So the coefficients, right? That means they can represent the moles level interpretation, like 2 moles of iron react with 3 moles of sulfur, making 2 moles of iron 3 sulfide. So the mole-mole ratio is a ratio of moles for any two substances in equation. So like the ratio between iron and sulfur, like 2 moles of iron, we need 3 moles of sulfur. Or for each 3 moles of sulfur, we need 2 moles of iron. So you can see here that sometimes, for example, the iron is on the top or is on the bottom. So depends, how do you know which one will be on the top or which one will be on the bottom? The answer is depends what the question is asking and depend what was given. For example, here. So let's say that we are going to do a calculation using molar ratios to convert from moles of A to moles of B. So first, like let's say the question gives the moles of one substance and use the coefficient from the balanced equation. We're going to convert to moles of the other substance. For example, here, the reaction of nitrogen gas reacting with hydrogen gas, the reaction here makes 2 moles of NH3, right? So, for example, how many moles of hydrogen are needed to produce 34.8 moles of NH3? How we're gonna start here? We're gonna start writing what the question gives. So the question gives 34.8 moles of ammonia. So right here, 34.8 moles of ammonia. Now, the question is asking the moles of hydrogen, and it gives the moles of ammonia, right? That means now we're going from moles of ammonia to moles of hydrogen. We're going to use this mole ratio, right? That comes from the balanced chemical equation, right here. So the question gives ammonia and is asking for hydrogen, right? So ammonia will be on the bottom. So we have 2 moles of ammonia here. And the question asks for hydrogen. So we're gonna put the ratio of hydrogen here. 3 moles of hydrogen on the top. So if you do this math here, 34.8 multiplied by 3 divided by 2, the answer is, so you can see that it cancels moles of NH3, moles of NH3. So your answer is gonna be 52.2 moles of hydrogen, right? And for example here, how many moles of iron are needed? The reaction of 12 moles of oxygen. Yes. First, make sure the reaction is balanced, right? So for iron, 2 times 2 for iron, okay. Oxygen, 3 times 2, 6 oxygens, and here 2 times 3, 6 oxygens, right? Okay, then let's start with the question. What the question gives us 12 moles of oxygen, so write here first, 12 moles of O2 times the ratio between what was given. The question gives oxygen, so it's right on the bottom, the ratio of oxygen and gas. So here, there's 3 here, 3 moles of oxygen and gas, right? So for each 3 moles of oxygen gas, you needed 4 moles of iron, right? The code of the ratio here. For iron, 3 oxygen. So if you do the calculation here, 12 times 4 divided by 3 will be 14 moles of iron. Then the next step is from grams to moles. So from grams to moles, you are going first take the grams given, divide by the molar mass to find the moles, right? The moles of A, for example, here. And with the coefficient from the balanced equation, are going to find the moles of the substance B. For example, here, still use the same equation, and the same chemical equation, that's Haber process, actually, NH2 plus hydrogen gas making NH3. And the question is asking, like, how many moles of hydrogen are needed to produce 34.8 grams of ammonia, right? What we're gonna do here first, write first what the question gives. The question gives 34.8 grams of NH3, right? After this step in grams, we are going to divide by the molar mass, right here. What's the molar mass of NH3? It is 17.04 grams per mole. So each 1 mole of NH3, you have 17.04 grams. Now, the question asks for how many moles of hydrogen are needed, right? To produce 34.8 grams of NH3. That means your ratio that you need is a ratio between NH3 and hydrogen, right? So the question gives NH3, so your NH3, so NH3 will be, the ratio will be on the bottom here. So you have 2 moles of NH3 that is shows here in the balance equation. So we're going to write right here, 2 moles of NH3, correct? Okay. Then the question's asking for moles of hydrogen. So your ratio of hydrogen, that in case is 3, you go to the top. Okay, so 34.8 divided by 1704 times 3 divided by 2 is equal to 3.06 moles of hydrogen gas. So this was from grams to moles. So the first part was from moles to moles, then from grams to moles. Now let's go from moles to grams. Correct? So let's see here. So from moles to grams. So here, this question asks, how many grams of hydrogen are needed to produce 34.8 moles of NH3? So again, write first what was given. So 34.8 moles of NH3. Then use the mole ratio to convert it from moles of NH3 to moles of hydrogen. So the question gives moles of NH3. So the number 2, right? So 2 moles of NH3, 2 moles are going to be on the bottom. And the 3 moles of ammonia, of hydrogen, it stays on the top. 34.8 times 3 divided by 2 will be divided by 2 and multiply. Right here, you have from moles of ammonia to moles of hydrogen, right? Okay. The question is asking from moles to moles, we would stop right here. From moles to moles. Like from moles of A to moles of B, You just need the moles numbers and the mole ratio from the balanced chemical equation, right? But the question is asking for what? From grams. The question asking for this question asks how many grams of hydrogen. So from moles of hydrogen to grams of hydrogen, what are you going to multiply by the molar mass? What's the molar mass of 82? Will be 202 grams per mole. So if you multiply 34.8 times 3 divided by 2 times 202, you have 105 grams of hydrogen, right? So we have here an example of this combustion reaction, right? Combustion is a reaction with a compound with carbon, burned with oxygen, making carbon dioxide and water. So here I wrote just for you guys to go from grams to moles divided by the molar mass, and from moles to grams multiplied by the molar mass, right? Okay. So in this combustion here, by the way, is a hexane. Calculate the moles of water. I wrote here water, formed when 2 grams of ethane react with excess of oxygen. Okay, so start with what was given. 2.0 grams of ethane. Ethane divided by the molar mass of ethane. The molar mass of ethane is 86 grams per mole, right? So if you don't remember how to calculate the molar mass, right? Each carbon is 12, so 12 times 6. The hydrogen is around 1, so 14. 14 times 1. So the molar mass of ethane is 86 grams. So from grams to moles, take the grams divided by the molar mass. And now, using the mole ratio between what question is asking for moles of hydrogen. So moles of hydrogen stays on the top. How many hydrogens you have? Sorry. The moles of, questions ask for the moles of water, right? You have 14 moles of water here. Sorry, it should be H2O, is water. And you have 2 moles of ethane on the balanced chemical equation, right? So there's 14 here, coming from here, and 2 moles came from ethane. So 2 divided by 6, right? To find the moles of ethane, and use the mole ratio to go from moles of ethane to moles of water. We're going to multiply by the mole ratio. It should be 0.16 moles of water. Why the answer should have 2 significant figures? Because the question here, the only data that you have, it has only 2 significant figures. Okay? And you guys can practice this one here. How many grams of oxygen are required to form 1.75 moles of water? So right first, start with what was given, 0.75 moles of water here. Then how many waters you have? What's the ratio between water and oxygen? So I have 14 moles of water and 19 moles of oxygen. Okay. Then the question is asking for grams of water. So from moles to grams multiplied by the molar mass. The molar mass of water is 32 because each oxygen is 16. So 1.75 moles of water times the ratio from the balanced chemical equation multiplied by the molar mass of oxygen gas will be, you'll be needed. The answer is 76 grams of oxygen are required to form 1.75 moles of water. Okay. Right, so now we saw from moles to moles, from grams to moles, from moles to grams. Now it's from grams to grams. So first, I would check if the reaction is balanced, right? So start with grams of what was given, grams of the given divided by its molar mass. I'm gonna convert from grams to moles. Then the mole ratio will be use the balanced equation to find the moles of what you want. And then to finally convert from moles to grams, you multiply by the molar mass of what you want, all right? And make sure always start with a balanced chemical equation. Then take the mass of the substance you are given and use its mass to convert to moles. So from grams to moles divided by molar mass. Then use the mole ratio to convert the moles of what you have to moles of what you want. How do you find the molar ratio? Use the balanced chemical equation. And finally, from moles to grams, you multiply by the molar mass. For example here, still using the same example, the same reaction, the question asks, how many grams of hydrogen are needed to produce 34.8 grams of NH3? So start with what was given, 34.8 grams of NH3, right? Divided by NH3 molar mass. So 34.8 divided by 17, using the mole ratio for the balanced chemical equation. So have 3 moles of hydrogen and 2 moles of NH3, right? So you can see here, grams of NH3 cancel out of grams of NH3, moles of NH3 cancel out with moles of NH3, and then you have here, right here, we convert from grams to moles, right? But the question asking for how many grams. So you are going to multiply the moles of hydrogen gas that you calculated here by its molar mass. The molar mass of hydrogen gas is 2.02 grams per mole. So you multiply here, you have the final answer that is 6.19 grams of hydrogen gas, right? From grams to moles divided by the molar mass. Then use the ratio from the balanced chemical equation, and then from moles to grams multiplied by the molar mass of what you want. The next topic here is limiting reactant. Limit reacts the reactant present in this smallest stoichiometric amount. In other words, it's the reactant you will run out of first. So in the example here, you are reactant hydrogen with oxygen. And here you have, after the reaction, you have water. So, but you still have molecules of oxygen in here. Why you have extra oxygen here? Because in that case here, the hydrogen was run out first and you have excess of oxygen. So before reaction, you have 10 hydrogens and 7 oxygen. And the after reaction, you have 10 molecules of water, by the white and red color here for water. And the 2, so the red head here, oxygen. And you have 2 oxygens in excess. and no molecules of hydrogen. So the white here, the hydrogen, and the red one are gonna be the oxygen. And this should be water. So the limit react is used in all stoichiometric calculations to determine amounts of products that are produced in amounts of any other reactants that are used in a reaction. So you guys can try to answer, to practice this question here. See if you get the same steps, the same answer. For example, problem 6. The most important commercial process for converting nitrogen from the air into nitrogen-containing compound is based on the reaction of nitrogen and hydrogen to form ammonia. So I still use the same reaction. So the question is, how many moles of NH3 can be formed from 3 moles of nitrogen and 6 moles of hydrogen? So to answer this question, you need to know which reactant is the limiting reactant. How we're gonna do this? You need to find which of these two reactants will make the smallest amount of the product. So let's follow the step. How many moles of NH3 can be formed from 3 moles of nitrogen? Let's go to this one. Let's call nitrogen reactant 1. So reactant 1, nitrogen, you have 3 moles of nitrogen, right? Here. And then using the mole ratio, right? The question gives here 3 moles of nitrogen. So your nitrogen, 1 mole, we're gonna stay here on the bottom. And the question is, so how many moles of NH3 will be produced? So the 2 moles of NH3 stays on the top. So we are going to make the math. 3 times 2. So if you have 3 moles of nitrogen, the reaction should make 6 moles of NH3. Okay, but we do not have the answer yet because we need to calculate which of these two reactants produces the smallest amount. So the second reactant, hydrogen, it says 6 moles of hydrogen, right? That was given here initially, using the mole ratio between hydrogen and NH3. So we have 3 moles of hydrogen and 2 moles of NH3, right? So 6 times 2 divided by 3, you have 4 moles of NH3. So how many moles of NH3 can be formed? So which one is the smallest amount? 4 moles, right? That means hydrogen is the limiting reactant, and the limiting reactant produces the smallest amount. So the question is, how many moles can be formed? So the answer is 4 moles of ammonia was formed because came from the limiting reactant. The limiting reactant is a reactant that produces the smallest amount is when the reaction stops. Right? And finally here, calculate the percent yield for stoichiometry problem. The theoretical yield is the maximum amount of product that it can be made. In other words, it's the amount of product possible as calculated through the stoichiometry problem. This is different from the actual yield. Actual yield is the amount that was actually produced and measured, right? So, okay, how to calculate the percent yield? It will be actual yield divided by theoretical yield times 100. So, for example here, the theoretical yield is the amount that was made from the limit to react. That means this problem here, this 4 would be your theoretical yield here. And calculated present yield will be the actual yield they're going to be given in the question divided by the theoretical yield, that is the one calculated, times 100. So, for example, I'm going to stop here, right? And then we're going to record a video showing the problems, right? So, practice problems here.